Chapter 1, Section 5, Physics Talk, Speed and Braking Distance, Negative Acceleration and Positive Acceleration. From your investigations in this section and the previous section, you observe that acceleration of an object is determined by how fast the velocity of the object changes with respect to time. This is represented mathematically with the following equation. Acceleration equals change in velocity divided by change in time. Acceleration equals change in velocity divided by change in time. The symbol delta stands for change in. This equation can also be written in the following way. Where A is acceleration, VI is initial velocity, and VF is final velocity. So acceleration equals final velocity minus initial velocity divided by change in time. The cart in your experiment undergoes a negative acceleration because the final velocity is 0 when it stops, which is less than its initial velocity. For an object stopping, final velocity equals 0. Therefore, acceleration equals 0 minus the initial velocity divided by change in time, which equals negative initial velocity divided by change in time. Recall that you read that sometimes people use the term acceleration to describe speeding up, and they use deceleration to describe something slowing down. In order to be clear about meanings in physics, the terms positive acceleration and negative acceleration are used. Positive represents one direction, and negative represents the opposite direction. Furthermore, an object could have a negative acceleration by decreasing its speed in the positive direction or increasing its speed in the negative direction. Imagine you are driving an automobile to pick up a friend to go to the movies. You know the street your friend lives on and the house number. You slowly drive down the street but accidentally pass your friend's house. Realizing your mistake, you slow down and stop. When you are moving forward at a positive speed but slowing down, the automobile has an acceleration backward, a negative acceleration. After the automobile has stopped, you check to see if it is safe and then start to back up with the automobile still pointing forward. When you start to increase your speed in the opposite direction, you are moving backward at a negative speed, and your acceleration is also backward, a negative acceleration, until you are traveling with constant speed in reverse. Here we go. As you slow down again to stop, when you are approaching the correct house, you are still moving backward, negative speed, but you now have a forward positive acceleration to bring the automobile to a stop. Finally, your friend gets into the automobile and you now pull away going forward with a positive acceleration until you are driving with a forward positive constant speed to the movies. All right, so this is the motion of your car. Okay, let me zoom out because it wants to look at the diagrams at the same time. I don't know if we can see this. But when you're looking at the PDF, you guys have this PDF in your Google Classroom. So when you're looking at the PDF, what it is diagram A, that corresponds to this. Diagram B corresponds to this diagram. So just when you're referencing that for yourself, that's how you're going to reference that. And that way you can scroll up and down at your own pace on that. Okay. In this example, you can see that a negative acceleration can sometimes decrease the speed of an automobile or increase the speed of an automobile, but it always decreases the velocity of the automobile by exactly 2 feet per second every second. All right. So again, you guys have these PDFs in your Google Classroom, and you can use that to refer to that previous chart. Calculating braking distance. Using the definition of velocity and acceleration, you can derive an equation for the braking distance when a vehicle comes to rest. The equation is shown below. Okay. So you have the final velocity of the car squared equals 2 times acceleration times braking distance plus initial velocity squared. I would put this all, I'd put the 2 times acceleration and braking distance in parentheses and solve that, and then add it to the initial velocity squared. And then that would equal final velocity squared. So you would actually have to take the square root of that to just get the velocity, the final velocity. All right. So we said the V subscript F is final velocity of car. Initial velocity of the vehicle is the VI. Here's where they're saying, notice it must be squared. This is the same as multiplying it by itself. So just initial velocity times initial velocity equals initial velocity squared. A is your acceleration. D is braking distance. Because the final velocity of a vehicle is 0 after a car comes to a stop, you may put a 0 in for final velocity, and of course 0 times 0 is still 0. So you have your 0 equals 2 times acceleration times distance plus initial velocity squared, or initial velocity squared equals negative 2 times acceleration times distance. You can use the helpful circle to solve for any of the variables in this equation as well. Of all the equations in your first year of physics, this one may have the greatest impact on your safety. Understanding this equation may one day even help save your life. From this equation, you can see that if you double the initial velocity, then the braking distance will have to quadruple. If you triple the initial velocity, then the braking distance will be 9 times as great. And you guys know that when you're if you're driving down some of these country roads and there's a tractor and it's going slower, and you need to make sure that, you know, if you pass it, that there's enough space in front of you, that there aren't any cars coming, and that that any car that would be coming would have enough distance to stop. You probably found in the investigate that doubling the speed increased the distance traveled while the vehicle was braking by about a factor of 4, and that tripling the speed increased the braking distance by about a factor of 9. Look at the data for the sports car. The speed increased by 1.33, while the braking distance increased by approximately 1.33 times 1.33 equals 1.77. Experiments completed with a great deal of care, ensuring that the braking acceleration is constant between trials, find that this relationship is true. The velocity squared relationship is derived assuming, let me scroll down so we can see the whole chart. Okay, the diagram, I mean. The velocity squared relationship is derived assuming constant acceleration, which is approximately true for real automobiles in everyday stopping situations. The velocity squared equals -2 acceleration times distance equation models reality very closely and is therefore useful for describing braking. How can knowledge of the velocity squared relationship save many lives? If you were to decrease your speed to 1/3 your original speed, you would need only 1/9 of the braking distance. If you double the speed, you do not require double the distance for the car's brakes to stop the car, but 4 times the distance. Decreasing your speed can save lives because of the significant effect of slower speed has on braking distance. So, the slower that you're going, the less braking distance. The faster that you're going, the more length it takes to stop. You have seen how equations can model the motion of an automobile braking. And an automobile with a negative acceleration can also be described using graphs of distance versus time, velocity versus time, and acceleration versus time, as shown below. Okay, so that's your distance versus time, velocity versus time, acceleration versus time. In the velocity versus time graph, let me scroll up a little bit because they're talking about the velocity versus time graph. Here it is. Velocity versus time graph. In the velocity versus time graph, you can see that the velocity is decreasing as the automobile comes to rest. Notice that at rest is equivalent to a velocity equal to 0. You should also notice that the slope of the graph is constant. This implies that the acceleration is constant since the slope of the velocity time graph is equal to the acceleration. Finally, notice that the slope is negative, sloping downward, which implies that the acceleration is negative. In the acceleration versus time graph, in the acceleration versus time graph, you can see that the acceleration is constant and negative. Constant and negative. In the distance versus time graph, you can see that the acceleration is constant and negative. Hold on a second. I'm sorry. In the distance versus time graph, you can see how the change in distance for a given time changes as the speed changes. Right here. Notice that the slope at the beginning times is very steep, corresponding to a large velocity, and toward the end, the slope becomes 0, corresponding to the car stopping. Thus, the graph is a curve.